So, so last time I have answered some of your doubts from the group. This time, try to do the same. Oh, hello. Yeah. Okay, so let's start. Let me share my screen from where I have started the last time. Uh, as you can see, last time we have talked about the circulation vector, Kelvin's vorticity theorem, that is valid for invisible incompressible barotropic fluids. So we have derived this equation. So omega is the vorticity. This is from the Stokes divergence theorem. And then so we have discussed everything else. Then we talked about the sample. Talked about the sample assignment problems, right? Yeah. So question number one was that this. So I'll give you some time to digest. So these are very simple, given that I'll give a little time to recap three things about this. So this is very simple, right? I have given the answer for you so that you can check with yours. The fluid has to be invested in compressible rotational. Secondly, I talked about this, how you can calculate the force. This is just a simple Newton's second law, as you see how the velocity changes, and the conservation equation is this Bernoulli's theorem. The total energy is constant. This will total energy, right? The pressure and the kinetic one. And then I talked about this on the character statement that viscosity will produce circulation fluids. think I discussed about this. But Okay, then yeah. So this you all have done, right? 4 and 5. 4 is just the mutual skew with the momentum equation. It will stick to the surface. Okay. Consider an inviscid monatomic ideal gas 1 mole. The specific enthalpy of the gas will be, as the formula suggests, last time I told you, but this I haven't told you, no? But no one have objected till now. So I think I'll left there somewhere. No. So let's get back to some of the more assignment questions. Okay. So the first question was, consider a smooth sphere immersed in a fluid that is steadily flowing past it in the positive direction at a speed u. As per an observer standing in the lab, there are no temporal changes in the flow. So temporal changes mean changes in time. So the partial derivative in time is tends to 0. Select the statement that are correct. So the first statement is reading like this: if the flow is perfectly inviscid, the tangential normal components of fluid velocity at the surface of the sphere are 0. Inviscid means, you understand, right? There is no viscosity. If the fluid viscous, the tangential and normal components of fluid velocity at the surface of the sphere is 0. So the question is related to the fluid velocity at the surface. If the fluid is perfectly inviscid, the fluid velocity u can be expressed in terms of the gradient of scalar potential phi, so that u can be expressed as minus of grad phi. If the fluid is viscous and incompressible, the fluid velocity u can be related to the Laplace equation involving the velocity potential phi, where square phi is equal to 0, with the appropriate boundary conditions. So I'll give you some hint. As you already have done the assignments, I'll still give you a hint, some hint that you can think of it. Like, so it is talked about the fluid is in a smooth sphere, smooth sphere that is immersed in the fluid, and the fluid is flowing in the positive x direction. The velocity given as u. So you are looking from the lab perspective, lab frame. So there are no timely changes of the flow. So the fluid is steadily flowing. Okay. I mean, yeah. So the delta is 0. So which will be the valid answer? Considering the fluid is inviscid and viscous. So I have already discussed with the Kelvin's volticity theorem and the Bernoulli's theorem. So you can think from those perspective. I'll give you some time to think. So uh, So let me give you the answer. So okay, so I have okay. So the flow is invisible. So first take the situation where the flow is invisible. So there is no viscosity. So in this Stokes equation, the viscous term is absent, right? And the momentum equation only contains part derivative of the fluid velocity. So therefore only one boundary condition is required on the surface of the sphere. So, okay, because uh, first derivative. So for the first derivative, there will come only one constant, only one boundary condition. So that's why it will be required. So this is the fluid velocity you can explain in terms of the gradient of scalar potential. So that IDS U is equal to minus grad phi. For the viscous flow, we need two boundary conditions. I think I have explained this earlier also. And the most commonly boundary conditions require the fluid to stick on the surface of the sphere so that both normal and tangential components are zero. Okay. So option B. If the fluid inviscid, it's irrotational. Okay, so that curl of U is zero. So curl of U thought can be expressed as a some gradient. Gradient will be zero. For viscous flow, this is not valid. Yeah, for viscous flow, it is not valid because the curl of U won't be zero. So the condition incompressibility is not relevant for this. If it is valid for incompressible, so incompressible means just that del dot U will be zero, right? So you can be related to the Laplace equation, which version of this on the valid. So option B and C are the right options. Just let me know how many of you have got this right. So So I think we have understood here the right options. If you don't, please let me know in the group section, or you can also comment on the YouTube video after I upload this. So there also you can be in touch with me. So let's move on to the next question. Okay, so I may have slightly uh, suffered the questions. So you see now the question number 4. So consider two Earth-like planets, 1 and 2. Both the planets have isothermal hydrostatic atmosphere. The atmosphere temperatures on the two planets are T1 and T2. Both the planetary atmospheres are under the influence of a constant gravitational acceleration g. You can assume that both the atmospheres comprise of fully ionized hydrogen, one proton and one electron. In atmosphere on, let the length scale over which the density changes by a factor of E be alone. The same quantity for atmosphere 2 is L2. Last time. It's 2 o'clock. From here we'll move on to a little fast. Okay, so option says on both cases the density will decrease with the height from the surface. This so imagine the scenario that two planets are same, like Earth-like planets. Okay, and the atmosphere are same, isothermal temperature is same, hydrostatic equilibrium, but the temperatures are different. Okay, so both the planetary atmosphere are under the influence of a constant gravitational energy. So fully and hydrogen is the same. Length is clear, the density changes by a factor of E, B, alone, and density changes. Okay, so the relation between the density. So what do you think? Which options will be correct? Option B and D, you can think that L1 by L2. So simply L1 T1 is equal to L2 T2. So LT is constant. So L proportional to 1 by T. That means option B is length is inversely proportional to the temperature. And option D is length is directly proportional to the temperature. So which one it should be? So more the temperature, more the temperature gradient, right? So let's give to the answer. So we know the pressure gradient. Simply, pressure is rho gh. So from that we know that dp d to dp dk is minus rho g as uh, direction is altered. So more that length will go upper, the density will decrease, pressure will decrease. Sorry, pressure will decrease. So that this is so you can see that rho is equal to 1 by z, right? Not that. And P is equal to this rho by mp kt. So if we replace P with this, we'll get that rho by mp forget mp, dp dz is dt dz, okay, and rho, sorry, temperature is constant, right? Okay, so d rho dz, and we'll get there the t 1 by t. So 1 by rho d rho dz is minus d by mp kt. Right, this rho will come there. So then it will get ln rho. So ln, so here you can see that the 1 by z and here 1 by t. So obviously L proportional to t. So L1 by L2 is T1 by T2. So option D is correct. Option A is saying in both cases the density will decrease with the height from the surface. This is obvious, right? As for Earth like atmosphere, it is valid that if we go further and further in the positive direction, I mean away from the Earth's surface, the density always decrease, right? And this says so. So option A and D are correct. So we go on to the next question. I think we have understood. Give some time to digest. So the next question is consider a circular pipe of diameter 2a filled with a various fluid. The axis of the pipe is oriented along the horizontal direction. Consider cylindrical coordinates so that r is equal to 0 denotes the axis of the pipe and r is equal to a denotes its surface. There is a uniform pressure gradient along the positive x direction applied to the field. Okay, so pick the statements that are correct. The fluid will accelerate in the positive x direction. The fluid will flow with an x-directed velocity given by uxr gxp minus r square by k square, or k is a constant. The fluid will flow with an x-directed velocity given by uxr k times a square minus r square, or k is a constant. The quantity dux dx is not equal to 0. Okay. So as you understand correctly this question, that the pipe is circular and the diameter is given to us. Radius is a. The axis of a pipe, there is a uniform pressure gradient along the positive x direction and dx applied to the fluid. Statements that are correct. The fluid will accelerate in the positive x direction. The fluid will flow with an x-directed velocity given by uxr exp minus r square by k square, where k is a constant. The fluid will flow. Okay. So you can read and understand the questions. So option B is saying the positive x velocity will be exponential. Option B is saying that it will be this form. And option D is saying it is non-zero. So here it is given that as r is equal to a, it can be 0. Here also r is equal to, so from to the, so the fluid is viscous, right? So the pressure gradient force, sorry, pressure gradient force will be balanced by the viscous frictional force. There will be no net force on a fluid parcel. Statement A is clearly not correct. Both the statements B and C look right in that the fluid velocity is maximum at the center and decrease towards the pipe walls. However, the boundary conditions mandate that the fluid sticks at the boundary. So the fluid velocity goes to 0 at the walls. Option C agrees with this. So yeah, statement D is clearly right for a viscous fluid, obviously. As you know that for viscous fluid, curl up is not 0. So C or D are right option. Mm, Okay. Next question. Consider a smooth spherical ball of radius A falling through an infinite viscous medium under the influence of gravity. Intuition tells you that it will stop accelerating after some time and will attain a steady terminal velocity. By conducting experiments on balls with various radii, you observe that the terminal velocity is proportional to a square. So all the balls are made of the same material, so that their densities are the same. So pick the correct statements. The drag force on the ball is proportional to A and proportional to its velocity. The drag force on the ball is proportional to A square and proportional to the square of its velocity. The terminal velocity attained because the drag force is equal and opposite to the gravitational force on the ball. So it is said that the ball is smooth and spherical and falling an infinite viscous medium. So the gravity will apply. The terminal velocity is said that is proportional to A square. Okay, that it is. So now the terminal velocity attains when something falls under the gravity, and the gravitational force will be balanced by its viscous force, so that it will attain a steady velocity and it won't accelerate anymore. So that is the terminal velocity. So as you can see in the diagram, okay, cylinder with viscous fluid flowing in positive direction. Okay, so the terminal velocity is reached when there is no force. Obviously, the drag force Fd is equal to gravitational force Fg. Okay, so gravitational force is proportional is mg, and that is proportional to rho a cube g. Okay, so then Fd. So suppose we take the drag force is proportional to a to the power p u to the power q. So it needs to match this. So u is also proportional to u square. So you can get here p plus 2 get 3. So on the choice sheet, it will work only for p is equal to 1, k is equal to 1, right? And the drag force on the ball is proportional to it, proportional to its velocity. So simply, okay. Moving on to the next question, that consider an incompressible fluid flowing through a pipe. The pipe is horizontal, but its cross-sectional radius is not constant throughout its length. In section 1 of the pipe, its radius is 2 cm and the flow speed is 10 cm per second. In section 2 of the pipe, its radius is 5 cm. Sections 1 and 2 are joined smoothly, so there is no abrupt transition. Choose the correct answer. You can see option A, B, C, and D are given. Okay. So this is similar to this question, if you remember. Uh, and from mass conservation, we get that V1A1 is equal to V2A2. So V2 if on is on 0.6 centimeter per second, and that is less than p1, right? So from Bernoulli's constant, we can get that P2 greater than P1. So option A and D are correct because the pressure in section 1 is less than pressure in section 2. Option A is fluid velocity in section 1 greater than fluid velocity in section 2. Right. Okay, so I'll give you some time here. Just So I welcome you all to today's session. So let's start from where we have ended the last time. So okay, so I have recorded the transcript for you also. So without further ado, I'll tell the brief key points from last lecture that we have talked about the Reynolds number and how we have defined that for in-visit and visit flows. So and I have also described the CD versus Reynolds number plot. And we have seen that the CD decreases with the Reynolds number, and after a very long and high Reynolds number, it shows another dip in the plot. So I will briefly mention some of those. Let me share my screen. So these are from last time. So I have mentioned Reynolds number and the vorticity equations and all. These are some of them. So see it correctly, then okay, so these are the problems I've discussed. So now I'll discuss the screen. So let's talk about the Katta-Joukowski lift theorem. So consider potential in conserved flow around a sphere. So this is for inviscid flows. This is called KJ lift theorem, KJL theorem, or Katta-Joukowski lift theorem. Okay. So then we get the del square phi is 0, and we know that phi as a function of phi and theta. So define the potential this form, and you are at r is equal to a. You can see the r minus r is r minus r square by r, so 0, and u theta r is equal to a. We'll get that it is r minus a, which is non-zero. Okay, so this is how it is defined, the potential form of this theorem. This is clear the radius a of the fluid is in a sphere. You see there's the lines are bent around this basically, right? So this is about the potential incompressible flow around the sphere. So, and if we add the circulation, there will be small viscosity keep between potential flow. So psi r theta will be u r minus a square by r sin theta plus gamma by 2x ln r by a, right? So there is a homework for you. So gamma is a circulation. So ur will be 1 by r del z del theta equal to u. If you just differentiate this equation, you will get this from sin theta, you will get cos theta, and then u theta and del psi del r will be this, right? This is theta and this is the r form. Then k, which is the circular integration of u dot dl, that is 8 from r to r on, directly on r minus a square by r cos theta dr, right? Minus this term's integration and this term. So k is equal to, we know the integration of cos theta is 0 and sin theta is also 0. And d theta is 2 pi, 2 pi, 2 pi cancel out, r cancel out, it will be just minus gamma. So gamma is the circulation. Ignore the sign, so it is basically the circulation. So a surface of a sphere where u is equal to u theta, surface where r is equal to a, we'll get that this is r minus a, okay, and this is r is equal to a, then on this will be gamma by 2ka, right? Using Bernoulli's equation, pressure surface stood in which flow, P at r is equal to a will be infinity plus half rho u square minus half rho minus 2u sin theta minus gamma by 2ka squared. Then this diagram shows you that sin x at 0, sin 0 0, and this is 3k by 2 minus L. This is basically the, you know all this, right? Sin pi by 2 1, sin 3 pi by 2 minus 1 is the sign. So net pressure gradient along y-axis. So you can imagine with a stream flow from the angle, it will be the net pressure under the direction, right? So this is the equation. So net force along y-axis. If you say y-axis, so the net force will be P dot dA. P at r is equal to a times a sin theta d theta, because this is the a sin theta from 0 to 2 pi. It will be P u rho u gamma. Compressive flow del dot u is not equal to 0. Propagation of density disturbances. Sound Cs square is equal to del P by del rho. For compressive flow, del dot U is not equal to 0. So propagation of density disturbances. Sound Cs square is equal to del P by del rho. Propagation of perturbations, split rho Pu into background plus TBS. It will be rho is equal to rho U plus rho 1. P is equal to Pu, P naught plus P1. P is equal to U naught plus U1. Work with a small perturbations sufficient to work at linear order. Background remains unchanged in space and time. Mass continuity equation. We know this del dot LD plus del dot rho is 0, right? From here, if we just replace rho with rho naught plus rho on, we'll get this. So rho naught del dot E1 is equal to 0, del dot on del T. Our equation rho del U del T plus rho U dot grad U is minus grad P. So from this, can tell that rho naught del U1 del T is minus grad PR. Using P1 is equal to del P del rho 1. So you get this grad square rho 1, the small oscillations equation. Similarly for this we get this. So at linear order, that means small pressure density perturbations always travel with only one characteristic speed and zero background velocity. Cs square is equal to del P by del rho, which is not equal to f omega. I think you understand this because so we're talking about the barometricity, right? So where the pressure is very small and the perturbation intensity is very small, so that it is at linear order. So the zero background velocity, this is the sound speed, is not equal to f omega. Fourier analysis for the dispersion relation tells us that rho is proportional to rho hat exponential of phi k gamma minus I omega t. So basically omega square is equal to c square by k square, right? Because k is equal to omega by cs. So phase velocity is independent of frequency. Remember this term, phase velocity are independent of frequency and sound waves are non-dispersing. Subsonic flows M is U by Cs less than 1. Quasi-hydrostatic duality is not approximately 0, determined by pressure gradient. Supersonic flow, M is equal to U by Cs greater than 1. Quasi-ballistic, independent of pressure gradient and BC. If an incompressible fluid is steady, it has to be a subsonic flow. Steady mass conservation at del dot rho u is 0, incompressible del dot u approximately 0. Thus, u del rho minus less than rho delta u. So delta rho by rho minus less than delta u by u. So steady momentum conservation becomes E dot grad u is equal to minus grad v by rho. So u delta u is equal to minus c is equal by rho delta rho. So then Mach number is much less than 1. This is the steady momentum conservation. So compressibility is saying that, or its lack of, depends on flow speed versus wave speed. Wave speeds can be super or subsonic in Euler frame. In Lagrangian frame, propagating perturbations are always sonic with respect to background flow in Lagrangian frame. Okay, but in Euler frame, it can be supersonic. Advection equation del rho del 2 plus rho naught del u1 del x is 0. So rho naught by Cs, this term will be 0. So if you add this term, it will become this, and subtract this from this will yield this term equal to 0. So u1 by Cs plus rho 1 by rho naught is conserved along x minus Cst. It will constant this line. So variation of u1 by Cs plus rho 1 by rho naught and the characteristic ddt of A is equal to del A del t plus del A del x dx dt is equal to del A del t plus Cs del A del x is equal to 0. So this is conserved along x plus Cst is equal to constant. Variation of u1 by Cs minus rho 1 by rho naught along the characteristic. So ddt is equal to del A del t plus del A del x dx dt. That means del A del t minus Cs del A del x is equal to 0. Okay. So E1 by Cs minus 1, this is conjugate along this line, and this plus sign conjugate is minus x minus Ct constant line. So why x minus Ct is constant in the forward direction? You have seen the, no? The omega t minus kx minus omega t. Kindly this equation, if you just multiply with k, so kcs will be omega. This is the kx minus omega t. So why this is constant? And so that j plus this term is equal to this. So I've always seen this, that this is constant in the forward direction. Why? We'll just get to see this. P is equal to rho to the power gamma. The parametricity, either P can be proportional, but we have taken the proportionality constant to be 1. So del P equal to P on gamma rho to the power gamma minus 1 rho 1. So gamma P by rho 1 by gamma P1 by P naught equal to rho 1 by rho naught. Q partitionalized by a diaphragm. So the P1, P2 pressure in region 1 and region 2. So T is equal to 0, P1 greater than P2. E1 is equal to U2 is equal to 0. Suppose diaphragm punctured. Suppose the diaphragm here is punctured now. Say forward wave propagates x is equal to ct, and a backward wave propagates x is equal to minus ct. X is equal to ct is this curve, right? Sorry, x is equal to ct. This is x and t. 6 is equal to ct is this one. Yeah, or you can say that this term, depending, you can say 1 by c, right? So and x is equal to minus ct will be this term, this and this, depending on the c or 1 by c. So the backward wavefront is a forward wavefront. So at P not J plus conjugate along the forward wave. So J plus at t is equal to 0 will be 0 plus 1 by gamma P1 by P2. P2 is the background affected puncture. J plus at xp will be P by Cs plus 1 by gamma P by P2. J minus conjugate along backward wave. So J minus at t is equal to 0 will be this minus 1 by gamma. J minus at xp will be this. So if you solve for UP and P, you will get from both this four equation for the piston. UP will start P, P start P, P not P start piston. And this will move like this. So you will get this. Start P,
It's 5 o'clock.
will be this. And P, J minus T is equal to 0, J minus 6P minus 1 by gamma V by Cs minus 1 by gamma P by P2. Three equation, three unknowns value for P, P naught, EP. At piston, J minus is equal to T is equal to U, J minus T is equal to 0. U by Cs minus 1 by gamma, P naught by P2 minus 1 by gamma. The Riemann invariance waves are not weak, not sufficient to linearize. The mass conservation del dot del T plus U del dot del X plus rho del U del X is equal to 0. So 1 by C square you will get this equation. For the momentum conservation you will get similar kind of the equation, this del U del T. These are all from the lectures. Combining this we will get this, right? So the quantity U plus F is advected forward with velocity U plus CS. This will be equal to 0. The quantity U minus F is advected forward to velocity CS minus U. What are the differences with the advection equation? These are for your homework problems. So please try to solve. I'll upload this now. So please try to solve this. So head on to the sample assignment problem. So the first question comes as consider a hypothetical Earth-like planet with an atmosphere of fully ionized hydrogen, which is stratified under the influence of a constant gravitational acceleration g. You can assume that the atmosphere is isothermal. If L is the length scale over which the mass density in such an atmosphere falls by a factor 1 by A, then what will be the correct option? L proportional to T, 1 by T square, or 1 by T square. So you will know that for the isothermal case, P is equal to P follows the ideal gas equation and the barometricity follows rho to the power gamma. Right. So gravitational stratified pressure will be dp dz is g, right? Okay. So the dp is 1 by p, dp dz is 1 by rho d rho dz, which is proportional to g by t. This here. Gamma is 1. So ln rho proportional to gz by t. So rho proportional to e to the power exponential of gz by t. So E folding length at z proportional to t. This is gz by t, so z is proportional to t. Option A. Okay. A drag force on a solid object immersed in a high Reynolds number flow is observed to suddenly decrease at a critical Reynolds number. This is known as the drag crisis. The drag crisis is due to the sudden drop of the Reynolds number at high Mach numbers, the boundary layer around the solid surface becoming non-laminar. Generation of the small vortices in the boundary layer, non-zero tangential velocity on the surface of the solid body. So if you follow the answer B and C, option A is obviously wrong, and so is option D, because option A is saying sudden drop of the Reynolds number at high Mach numbers. The drag force on solid object is the high Reynolds number, so there can't be sudden drop of Reynolds number. Okay, the drag crisis is not due to that. Option D, non-zero tangential velocity, which is also wrong. The drag crisis is due to the onset of the turbulence in the boundary layer. The turbulence also creates vortices in the boundary layer. Okay. So boundary layer on the solid surface becoming non-laminar and generation of small water in the boundary layer. These are right options. Next question is pick the correct statement. Vortex setting increases drag on a solid body. A solid body moving in a perfectly invisible fluid will not feel a drag force. The pressure distribution on the surface of a spinning spherical ball in an invisible fluid is asymmetric. The pressure distribution on the surface of a spinning ball in an invisible fluid is asymmetric. So option C, the pressure distribution on the surface of a spinning ball in an invisible fluid is symmetric. This is wrong because this is asymmetric, right? Because the initiation of vortex setting is the processes which increases the drag at high Reynolds number until the drag crisis sets in. Okay. Option B is quite obvious because solid body moving in a perfectly invisible fluid will not feel a drag force. Obviously, because this is valid for fluid. The spinning ball will feel a lift. In other words, the pressure is different on the top and bottom. It is asymmetric. So option A, B, and D are correct. Consider the next question. Consider 2 points A and B inside a gas fluid with a constant velocity. A and B are not close to each other, but pressure fluctuations generated at A can reach B. Choose the correct statement. The flow between A and B is supersonic. A and B are causally connected. The frequency of sound waves heard by an observer moving with the fluid will be the same as that heard by an observer in the lab frame. The frequency of sound waves heard by an observer moving with the fluid will be different from that heard by an observer in the lab frame. Okay. So 2 points can be inside the gas flowing with a velocity. So they're not close to each other. So the pressure fluctuation generated A, so that can reach B. So to rectify this, you can see that the flow between A and B can be supersonic, where they're flowing with a constant velocity. Since the pressure fluctuation can reach from A to B, and they are causally connected, and the flow between them has to be subsonic because they are connected, right? It can be supersonic. Okay. Since the fluid is moving, there will be a Doppler shift. So the frequency of sound waves heard by an observer moving with the fluid will be different from the heard by an observer in the lab frame. So Doppler shift is there. A and B are causally connected. Yeah. So it is not supersonic, it is subsonic. The frequency of sound wave not same. The Doppler shift. So option B and D are correct. Consider the following on-day advection equation: del alpha del t plus u, del alpha del s equal to 0. Where alpha is some parameter, u is the on-day velocity. Pick the correct statement. Alpha is conjugate along the characteristic curve h equal to x minus ut. Alpha is conjugate along the characteristic curve b is equal to x plus ut. One can construct an ordinary differential equation from the advection equation with b square independent and a square independent. So either a and b or and c and d can be correct. See, remember this is plus, so obviously a is correct. Looking like this, but let me show you that tan in alpha x minus ut is constant. Okay. Next thing is del alpha del t. If we do this, will be 0. Del alpha del b will be 0. So del alpha del b square proportional to del alpha del b square is 0. So del alpha del b square 0. Okay. So option C and D both are correct. So next question number 5. Consider a set of undecoupled equation. Decoupled equation. Coupled equation means if one and if one consider if one has if and both it's x and t, and this is also. So if one is equal to this and this is equal to 0, this set represents heat equation, wave equation, nonlinear, none of the above. I think you can guess. But still heat equation is del f del t, a del square f del x I square. Wave equation del 2 f del t square is equal to del t f del x I square. Nonlinear equation is del f del x is equal to f square. So given del f del t plus 3 del f del x is f1 and this 0. So if we take in the partial derivative the time, we will get this plus, because f1 is this, right? So replace, so put the value of f1 in this equation, we'll get this. and this will be del 2f del t2, and c del 2f del x del lt. So this will be 2a term, and c square del 2 del x2. So we'll get this. So you can see that this doesn't follow the head equation, not wave equation, or non-linear equation. The mix of them. To couple the equation to see the only possible answer is D. Okay. So these are the options. So till now we reach here. So this question is very easy. You have to remember the heat equation where del f del t is this is the single derivative. It will be equal to double derivative of x. And here the wave equation is you see in the del 2 some parameter del 2 a del square f. Right? There will be some constant term. There can be some constant term beforehand like k square or lambda square. It doesn't matter though. There can be c to match the dimension. Obviously there will be c. But x is equal to ct. So there will be 1 by c square and your term. So nonlinear equation, there will be nonlinearity. So this follow del 2a del t2. There will be this combined coupled term. So this is followed a mixed equation. This is basically damped or forced equation, and that topic is out of the scope for this course and session. So we won't discuss that. Yeah. So let's look at the other thing. This question is question number 4. We also following the one and Vixen equation. And then we have number 4 del for del t plus u. Okay. So and then the question number 3, inside the gas flow in the constant velocity push each other but pressure fluctuations can reach there. So you can understand. Suppose in fluid there is some fluctuation at some point, and this that will if that reaches immediately then another point, so that means the fluid is subsonic. So before the information gets there, the fluid is connected, so the pressure is balanced. So that's why for coily connection there should be subsonic, and velocity will obviously be there. The question is simple if you think that way. The vortex setting you have to understand the idea of this, and this question the drag crisis. You have to drag crisis, vortex setting, is a very important phenomena, and this will uh, lead to the idea of turbulence. If you do any further course on turbulence and nonlinear physics, you need to know all of this. I mean, in astrophysics, you will need this. This will be helpful. The upcoming ones. So yeah, still now we have discussed this, and this is the sample where the length scale is proportional to the temperature. You have done this in the earlier session also. That's all from this. Okay. So I think you understood. So if you have any question, please let me know. I'll be waiting for some time for your question. And for this now, I'll recap some of the earlier portions. That helps. The earlier sessions. Okay. So Uh, So the next question says, on the key steps in linearizing is neglecting the product of small quantities. For instance, linearizing the momentum equation, rho naught plus rho 1 del u1 del d plus rho naught plus rho 1 e1 dot grad e1 equal to minus grad p1. Okay, so the product of small quantities. So for instance, linearizing the quantum equation rho naught plus rho 1 del E1 del T plus rho naught plus rho 1 E1 dot grad E1 is minus grad rho P1. To neglect the second term on the LHS, consider a body that measures 10 meter atomic cube moving through a medium. The typical macroscopic time scale for the problem is 2 minutes. How large would the velocity disturbances A1 have to be so that the linearizing assumption is not valid anymore? So there is a hint that you can use approximate like del t approximately 1 by t and del x approximately 1 by l, and L are not representative time scales and length scales. So E1 is greater than equal to 0.83 meters per second, and these are the options. So suppose that E1 dot grad E1, the order of E1 is square by L, right? And del E1 del T is and del E1 and del E1 del T. In other words, for E1 exceeding L by T, 10 by 2, so 5 meters per minute. Okay, so option C or 0.083 meters per second. Both are the same, just minute conversion. So assume that the dense plasma at the center of the sun is made up of equal number of density. These are the questions we have this. So the given that pressure at the center of the sun is around, so we know the rho is 129 gram per centimeter cube. That is 6 nmp. So rho will be the 6 nmp, which gives n is equal to, because rho is nmp, right? And we have the 6 number. So which gives n is equal to this, p is equal to, nkt. So which gives the value of p to 9 per centimeter square. If you convert that to atmosphere, we'll get 2.84 because on 9 per centimeter square 1.013 10 to the power 6, right? One atmosphere is equal to the sound speed gamma p by rho to the power half, that is 181 kilometer per second. Option B and option C both are correct. Consider two sources of sound that are equidistant from and stationary with respect to an observer. Source A emits sound waves at 1000 Hz while source B emits at 10,000 Hz. Pick the correct statement. The observer will hear source A earlier than source B. The observer will hear source B earlier than source A. Observer will hear this. So we know that this is a Doppler effect. Sound waves are always longitudinal. Sound waves are dispersionless. All frequencies travel at the same speed. So observer will hear both sources simultaneously. Okay. So they are equidistant. Consider two very large containers A and B filled with nitrogen. The temperature of the gas in container A is 4 times that in container B. The number density in container A is lower than that in container B. So here the correct statement. The adiabatic sound speed and it's called, which is the small and large. So the square of the adiabatic sound speed is gamma p by rho. You see C square is gamma p by rho. And p is equal to nkt, right? And rho is equal to nm. So n cancels out gamma kbt by m, where rho is the gas density. Number density, we know these factors. M is the molecular mass of the gas, K is the Boltzmann's constant, T is the temperature. So the sound speed depends only on temperature. We know that, not on the number density. Sound waves are longitudinal, so density displacement due to sound waves are in the same direction as that of the direction of sound propagation. So that is longitudinal. Option B, that the adiabatic sound speed container is 2 times larger than that in container B. Okay. In both containers, the density displacement due to sound waves in the same direction. Okay. So we have this, because this is the 4 times, in the square root over 4 is 2. In the correct statement, very subsonic flows are approximately hydrostatic in nature. Highly supersonic flows can contain discontinuities such as shocks. Highly supersonic flows are affected by large scale pressure gradients. The initial term in the momentum equation determines the pressure gradient term for subsonic flow. So very subsonic flows are approximately hydrostatic in nature, we know this, and highly supersonic flows can contain discontinuities such as shocks. Okay, I think we have already come across these terms like shock, so you'll understand this. They're very basic questions and equations. That this is the very important thing. The density displacement due to sound waves are in the same direction that of the direction of sound propagation. Please try to remember this. And these are the other equations. So I hope you have had a good session and I'm being able to tell you the things I wanted to. So okay. Thank you. So let's next time. Okay. Bye. Thank you.